So we took the midterm exam the last week. So how was the exam? I see. So usually the midterm exam of this computer architecture course include until the single cycle processor design. So it include the introduction to the computer architecture and performance, instruction set architecture, and then some basic of assembly language, and computer arithmetic, and the single cycle processor design. Usually the first half of this course is easier than it's easier than the last half of this computer architecture course, because the last half of this course will include the pipelining design, and then memory hierarchy and virtual memory. So as I said, the highlight of this course is the instruction set architecture. So it was included in the midterm exam. And then also another two highlights of this course is the pipelining design and memory hierarchy or cache organization. So usually the midterm exam is easier, but so actually I taught this course three times maybe. So usually the exam was the closed book exam. So actually this semester's exam was the open book exam. So I slightly raised the difficulty level of the exam, because this was an open book exam. So maybe the questions may be slightly difficult. 예, 어쨌든 이 중간고사를 오픈북으로 이제 봐서 조금 사실 오픈북이라고 하지만 시간이 문제죠. 시간이 문제인데, 어쨌든 이게 시간을 확보하기가 좀 어려워서 뭐 그런 문제도 있었다라고 생각이 들긴 하는데요. 예. 어쨌든 제가 이제 exam을 문제를 좀 이제 만들고 이제 TA한테 좀 검토해 달라고 부탁을 했을 때 좀 어려운 것 같다라고 했는데, 예, 좀 그랬던 것 같습니다. 평균은 아마 올라와 있을 거라고 생각이 되는데, so actually our TAs complete the grading of this midterm exam, and then they posted the scores on the Blackboard, and then I believe you can find your score and mean and median of this midterm exam on the Blackboard. 네, 블랙보드에 아마 절대평가, 절대평가라는 그러니까는 그러니까는 A라든지 B의 그런 뭐랄까 퍼센티지는 정해져 있지는 않지만, 어쨌든 거기 스코어에 맞춰서 제가 좀 성적은 이제 조절을 하고요. 아마 성적은 다른 과목하고 비슷한 레벨로 나가지 않을까, 그렇게 생각을 하고 있습니다. So okay. So and then this time we will learn about the pipelining design. So as I said, this is the highlight of this course. So in the previous class, I believe it's somewhat it's somewhat long from the previous class, but in the previous class we learned that what is the issue of this single cycle processor design? It was a performance, because in the single cycle processor design, the instruction of the computer instructions are executed in every cycle. So that means a single instruction is executed every cycle. That means only one instruction can be executed during one clock cycle. So CPI for this single cycle processor is the CPI. It's 1 because only one clock is consumed for a single instruction. But what was the problem? This is the hardware. So we need to consider the delay of the data path element of this single cycle processor design. So actually the delay was included in the last question of the midterm exam. So the delay is the critical. Delay is the critical issue because the delay of the critical path determines the clock period of this single cycle processor. And then if this delay of the critical path is long, then we need to set the clock frequency as low for to meet the delay of the critical path. Then the clock frequency will be low. So that if the clock frequency is low, so this is the very important equation. The execution time is the instruction count, CPI, and then multiply by clock period. So for this equation, CPI is 1, the instruction count is the same because the instruction count is determined by software and compilers. And then this instruction count, so how do you cannot change the instruction count of the software, right? So this is the fixed value. CPI is 1 for the single cycle processor, but the problem is that TC will be very long. So instruction for the single cycle processor, the performance is determined by this clock period, but because in the single cycle processor, the critical path, the delay of the critical path is long. That means the clock period will be also long. And then another issue of the single cycle processor is that the data path element is not utilized well. So as we saw in this analogy, this is single cycle processor design, each data path element like this, each element is not utilized concurrently. So that means during a certain period of time, a certain data path element is not used. So that is the resource of this hardware is wasted. So that's why the single cycle processor design, for the single cycle processor, the performance is low. And then for the pipeline design, we can reduce the delay of the critical path like this. So we can use the fast clock. So that means we can reduce the period of this clock signal, then we can reduce the execution time of the application. The ideally CPI is 1, but in this time, so in the today's class, we will learn about the hazard. So because of the hazard, the CPI of pipeline processor is larger than 1 actually, but usually for the ideal pipelining design, the CPI is also 1. And then the clock period is reduced. So that means the performance can be improved. So that is the benefit of the pipeline design. And it's very critical for the actually for digital system design, because the most of the digital system design implements the pipelining. Because without pipelining, we cannot handle this very long delay of critical path. Okay, so that's why the pipelining is so critical for this hardware design. Actually, this slide just compare the reduce the RISC-V ISA and then the other CISC type ISA like x86. So as we learned, the RISC type ISA is very simple and well organized. Also, the instruction width of this RISC type ISA is usually fixed, So that means for the RISC-V, the size of a single instruction is 4 bytes. That means 32 bit. But for other CISC type ISA such as Intel x86, that is the representative CISC type ISA, and then these x86 instructions have various lengths of instructions, like 1 to 17 byte instructions. So that means the instruction is very complex. So that means actually the single cycle processor, we designed the instruction decoding logic and controller unit. And then this instruction decoding stage and the controller unit is designed based on the instruction formats. So that means this controller unit or instruction decoding of RISC type ISA is simple comparing to the CISC type ISA. And then that means the CISC type ISA requires very complex instruction decoding and controller units. So that means the hardware will be very complex. That means the hardware will occupy the large number of transistors. Okay, that's why the RISC type ISA is better for higher performance. Okay, if the hardware if the hardware complexity is increased, then we need more transistors or more complex hardware units. That means the delay of this hardware unit is also increased. So this delay is very critical for the performance, as we learned, and so that's why the RISC type processor is better for the performance. Okay. And then let's learn about the hazard. This is also a very important topic in the pipeline design. So the hazard, what is the definition of a hazard? So hazard means the situations that prevent starting the next instruction in the next cycle. That is the definition of hazard. So what does that mean? So this is the processor, and then processor receives instructions. Actually, we assume that a processor can receive a single instruction every cycle. So that means the cycle number 1, this processor can receive instruction number 1. In the cycle number 2, then this processor can receive instruction 2, 3, instruction number 3. Something like that. That is our assumption. And then it is also true for the single cycle processor. Single cycle processor can receive a single instruction every cycle. Okay, but what is the hazard? By some reason, this CPU or processor cannot execute instruction every cycle. That is, and then this situation is called hazard. Hazard. So when hazard happens, a cycle is wasted. Okay, that is the definition of a hazard. So hazard means, so simply, so you can memorize that hazard is a situation that the processor wastes a cycle. By some situation, the processor, when a processor wastes a cycle by some situations, then this situation is called hazard. So actually the reason of waste of cycles. Okay. So this is very important because why is this important? Because of this equation. Execution time, IC, CPI, TC. So with the pipeline architecture, we can reduce this clock period. Then IC instruction count is the same. It's a fixed about the CPI. So we assume that this is nearly 1, but because of hazard, so when hazard happens, the clock cycle is wasted. So that means during a certain clock period, a processor cannot execute an instruction. So the CPI will be larger than 1 for pipeline architecture. So because of hazard, CPI can be increased, so the performance can be degraded. So that's why we need to know about the reasons of hazard in the processor design. And then also we need to reduce the number of hazards that happens in the processors. Okay. And then there are 3 types of hazard by the reason of hazard. The first type is the structure hazard, and then the second type is data hazard. The third type is the control hazard. So this means that structure, data, and control represent the source of hazard. So that means it indicates the reason of hazard, so why hazard happens in this processor. So what is the source of the structure hazard? That is the reason. What is the reason of structure hazard? That is a required resource. A required resource is busy. So that means, so we learned about the data path elements, and then the data path element process a certain steps of executions. And then if this data path element is busy, then this data path element cannot process an instruction. So instruction need to be pending because the required hardware resource is busy. So and then that is called the structure hazard. And then data hazard. So data hazard happens because of data dependency. So what is the data dependency? It's like A equal B plus C, and then D equal A plus 1. So in the high-level language program, so this program is executed sequentially from top to bottom. And then, as you can see, this second line statement requires the data stored in variable A. But this data in variable A is determined by the first statement. First is A equal B plus C. So that means this statement cannot be executed until the A is computed. Well, you may think, oh, that is obvious. So you may think, oh, that is obvious. So in the C program or Python program, the program is executed from top to bottom. Oh, then we can wait until the A is computed, right? But the pipeline architecture, the pipeline architecture flows 5 stages, and then actually for this statement we can use the add instruction. The final result of add instruction is stored at write back stage. That is the last stage of pipeline architecture. But for this statement, it will also it will be translated into add instruction. But this add instruction will read data from ID stage. That is the second stage of pipeline architecture. And then because of this different timing, when this instruction requires data in the ID stage, this data does not exist in the register file because write back stage is the last stage of pipeline design. So actually the computer processor wait until this data is stored in the register file. And then this phenomenon is called data hazard, because pipeline processor needs to wait until this instruction is completed, right? So wait means that the clock cycle is wasted. This is the data hazard, and then control hazard means that the clock cycle is wasted due to branch instruction. So for the normal instruction like add, sub, so actually the PC of this, the PC becomes the PC plus 4 for the next instruction, but for the branch instruction, the PC will have some different values, right? And then actually, we can know the result of the branch instruction when these values of the branch instruction is executed in the EX stage. So in the single cycle processor design, we learned that for the branch instruction, like BQ reads values from the register file, and then these values are compared in the ALU, and then if these two values are equivalent, then the PC is updated by PC plus target of the branch. It's like this. So it is also included in the midterm exam. So the processor need to wait until this target of the branch or the condition of the branch is reserved. But for the normal case, the instruction is fetched in the instruction fetch stage. That is the first stage of pipeline architecture, pipeline processor. So because of this branch instruction, then we don't know which instruction will be fetched for the next instruction, because there are two cases: the very next instruction or the instruction pointed by target of branch instruction. And then this result is determined in the EX stage. So it will take time. So usually the computer processor need to wait until the branch is resolved. That means I said wait. That means the clock cycle is wasted. That is the hazard. So it is called the control hazard because hazard is caused by control instructions. Okay. So there are three types of hazard. And this is also very important. So you need to memorize these three types of hazard. Okay, let's see the structure hazard. So as I explained, structure hazard is caused by lack of available hardware resources. So hardware is just the hardware. So it's the real thing. So if there is no available hardware resources, then instruction cannot be executed. That means the following instruction need to wait until this target hardware is available. So I said wait. So that means the clock cycle is wasted. So the clock. That means the clock cycle is wasted. It's the lack of hardware resources. But this very simple pipeline architecture design, there is the structure hazard will not happen. Also, in the single cycle processor design, the structure hazard will not happen also. So it is because in the single cycle processor design, only one instruction is executed during a clock period. So that's why, and that means only one instruction will demand the hardware resources. So it is only used by one instruction, so there is no source of the structure hazard. Also, in this 5-stage pipeline processor design, there is the structure hazard will not happen. Because as you can see, so that is the 5 steps of pipeline architecture as instruction fetch, register read, ALUOP, memory access, and register write. And then if we see the required hardware for each stage, so what is the required hardware for instruction fetch? Is instruction, memory, register read, so register file. But we will only use the read port, right? And then ALU, the instruction will use the ALU. The memory accesses, here's the data memory, then register write. So register file will be used, but the write port will be used. So that means for each stage, the unique hardware resource is utilized. So that means there will be no structure hazard. But if the instructions and data share a single memory, so I said that instruction is also handled like a data. So actually in the computer hardware, these all instructions and all user data is stored in the DRAM. The DRAM is the external memory. But in the processor, we separate the memory into two types of memory, like instruction memory and data memory. Why? in order to avoid structure hazard. So if we use only a single memory for instruction and data, what will happen? So instruction memory is required for instruction fetch of a certain instruction. And then actually this every instruction is read from the instruction memory because instruction fetch is applied to every instruction, right? Applied for every instruction. So actually the instruction for every cycle, the instruction memory is accessed. But how about the data memory? The data memory is accessed by load and store instructions, right? Only load and store instructions access data memory. So if the if the processor has only a single memory that shares instruction and data, then this port is requested by every instruction, every cycle. Then when the data is requested in this memory, then this instruction fetch cannot be performed because this memory should be used for data access by load and store instructions, right? So, and then this is, so if the instruction fetch is delayed, then actually every instruction requires instruction fetch stage. So the instruction fetch is delayed, then the clock cycle will be delayed. Okay. So if the processor has only one type of memory, then structure hazard can happen. Do you understand? Because the same memory can be requested by instruction fetch of every instruction and data access by load and store instructions. But in order to avoid this situation, we already separate the memory, the two parts, the instruction memory and data memory. And then the instruction memory is accessed by every instruction and every clock. And then data memory is accessed by load and store instructions, right? So the reason is that in order to avoid structure hazard, okay? 예, 맞습니다. 듀램은 이제 프로세서의 바깥쪽에 있어요. 우리가 이제 메모리 하이라키에서 이제 배우긴 하겠지만, 듀램 그 메인 메모리, 듀램은 프로세서의 바깥쪽에 있고, 여기 이제 우리가 말하는 인스트럭션 메모리랑 이제 데이터 메모리는 프로세서 내부 안에 있는 메모리를 이제 말을 하고요. 또 정확하게 말하면 이거는 우리가 캐시라고 말을 합니다. 그러니까는 뭐 지금은 이제 따로 이제 존재한다라고 이제 배우지만 결국에 이제 메모리 하이라키에서는 이제 하나로 익스터널 메모리가 이제 따로 있고 그게 이제 듀램이고요. 그렇지만은 지금은 프로세서 내부에서는 이렇게 이제 스트럭처 해저드를 피하기 위해서 그 따로 이제 메모리를 이제 만들어 놓고 사실 이 메모리는 진짜 메모리라기보다는 캐시, 그 템포러리 메모리라고 이제 보면 되겠습니다. 그 separate data cache. 네, 그렇게 이제 생각을 하면 되고요. So as I mentioned, this pipeline architecture design, the structure hazard will not happen. But if we use a single memory, then structure hazard can happen. Okay. And how about the data hazard? So data hazard is caused by data dependencies observed in our normal program. And then, as I mentioned, actually the data dependencies are frequently observed in our normal applications, because when we calculate some data with our high-level language, then data is actually the data of the former statement is usually utilized by the following statement of our program code, right? And then, so data dependencies are frequently observed in normal applications. And then due to this data dependency, data hazard can happen in processor. So this is the example of the data hazard. So as you can see, is X19. X19 is the result of add instruction. That this is the former instruction. And then this data in this X19 register is read by sub instruction, subtract instruction. So let's see the let's see how this add instruction is executed in the pipelined processor. So this is the clock cycle. So in this hardware, the clock period is 200 picosecond. So we can set, so clock count 1, so clock count 2, clock count 3, clock count 4, 6, 5, something like that. We can number the clock count number at every this clock period. So for this add instruction, as you can see, the add instruction need to write data to X19 at write back stage. So let's see the how this add instruction is executed. So add instruction is fetched from the instruction memory during the CC1, clock count 1, and then it is decoded the ID stage at the clock cycle 2. And then it is executed. The add instruction is applied by ALU at clock cycle 3. And memory is not accessed by add instruction, but this is the pipelined architecture. So add instruction need to flow the memory stage. So during the clock cycle 4, add instruction is in the memory stage, like mem. Even though this data memory is not accessed by add instruction, but add instruction is here. And then finally, at clock cycle 5, the add instruction, the result of the add instruction is written back to the register file. And then this sub instruction is actually the very next instruction of this add instruction, right? So in the pipeline architecture design, sub instruction will be fetched in the at CC2, the clock count 2, right? Because it's the very next instruction. But what will happen? Let me change it up. Okay, so this sub instruction will be in ID stage, the instruction decoding stage at clock cycle 3. But what's the matter? The required result is the required data is the result of this add instruction, and then actually the result of this add instruction will be written in at CC5. But the sub instruction try to read this required data at CC3. But the data is not ready in the register file, right? So sub instruction cannot be executed. So if this sub instruction is executed, then sub instruction will use the incorrect data. Then the computer processor will generate the incorrect result. And then if the computer processor generates the incorrect result, then we cannot use this computer processor, right? So this sub instruction needs to wait until the result of the add instruction is returned back to the register file as CC5. So that's why the sub instruction, the ID stage of the sub instruction is shifted to the CC5 here. And then finally, the sub instruction can be executed at 66. Okay. So what's the matter? In order to execute this sub instruction properly, then the computer processor need to wait 2 clocks. So problem is that we assume that the sub instruction can execute the next of this add instruction, but the 2 cycles are wasted. So actually we assume that every instruction consumes only 1 cycle, but this sub instruction consumes 1 plus 2 cycles, because this due to data dependencies and then data hazard, the sub instruction need to wait 2 clocks, additional 2 clocks. So the consumed number of clocks by the sub instruction is 1 plus 2 equal 3 clocks. So 1 instruction consumes 3 clocks. So CPI will be increased. So that's the problem. So due to the data hazard, the computer processor wastes additional clocks, then it will decrease the performance of this computer processor. Okay. But we can overcome this performance degradation with data forwarding. So this is also very important concept of the pipeline architecture. So what is the data forwarding? So let's see this example. So it's another add and another sub instruction. But so actually, the result of this add instruction is generated here, right? It is not written back to the register file during at this CC3 because it's not write back stage, but we know the result is already calculated by this ALU at this timing, right? So that means actually the computer processor has computed result by this add instruction. So what is the problem? Even though the computer processor has the result of this add instruction, but this add instruction will be written back to the register file at CC5. So this clock period. So that means the processor already has required data, and then this required data can be used by next instruction. How? If there is a path from here to here, so this is the very next sub instruction, and then we already know that this sub instruction will use ALU. Then ALU has 2 inputs from register file. So actually, this generate data can be used by ALU of sub instruction at this timing. Do you understand? So the result of add instruction is generated at this timing, and then the result can be used by this sub instruction, actually by ALU at this timing. Right. So as you can see, this time is the future of this this timing when the result of add instruction is generated, and then the computer processor already has this computed value. And then if there is a path, so data should be delivered to the input of the ALU, right? So if there is a path from this output of the ALU to the input of the ALU, then the next instruction can use the data generated by previous instruction. Okay, so, and then this is called the forwarding or data forwarding. And then, so sometimes this there, and when the data forwarding is applied, then we can avoid data hazard, because the sub instruction can be executed at the next clock of add instruction. Okay, so with the data forwarding, then we can avoid the data hazard, so we can increase the performance of pipeline processor. Okay. Yeah, it's a very good question. Is forwarding automatically detected by the hardware? It should be automatically detected by hardware. So that means the hardware need to support the data forwarding. So that means we need to design this forwarding path from the output of the ALU to the input of the ALU to support this data forwarding. And then it will be included in the lab, lab assignment 4. Okay. Now, but how about the load instruction? But the data forwarding cannot be always applied. Why? Because of load instruction. So like A equal 1. So in the high level language, like A equal 1 and then B equal A plus 2. How about this statement? So for this statement, we just load. So it's a load because the data is loaded to the variable. And then in the next instruction, this data is used for add operation, right? So we frequently use this type of statement, right? How about the load instruction? So in this case, in this example, the CC 1, 2, 3, 4, 5, 6. Okay. So when this load instruction is executed, the data is read at this point, right? At this point, because the data should be read from the data memory here at CC4. So data is read from here, but when the sub instruction is executed here, instruction fetch, instruction decoding, and then EX. So in the previous example, the data is generated here, and then data is used because it's a CC3 and then CC4. And then data is used at CC4, the first, the early of the CC4. But how about this case? This is the very first of the CC4, so CC4, right? But at this timing, the data is not ready. Why? The data will be generated at this timing. So this timing is the future of this timing, right? So this data cannot be used by this sub instruction during CC4. So in this case, we need to delay the execution of the sub instruction by 1 cycle. So the EX stage of the sub instruction should be here, like here, because the data will be ready at this timing. And then this data will be forwarded to the input of the ALU at CC5. So what's the problem? If the former instruction is load instruction, and then the next instruction requires data from this load instruction, then the next instruction will consume 1 more cycle, because the next instruction need to wait until the data is read from data memory. That is the fourth stage of pipeline architecture, pipeline process, right? It's very important, okay? So in this case, the sub instruction cannot be executed at the very next clock. So sub instruction will consume 1 clock plus 1 additional clock. It will consume 2 clocks. And then this data hazard cannot be avoided. So this data dependency, we can avoid data hazard for this data dependency from add to sub, like R-type instruction to R-type instruction. So if we implement the data forwarding path in the pipeline architecture, then we can avoid the data hazard. But if the former instruction is load instruction, then we cannot avoid data hazard. So in this case, the next instruction need to wait 1 clock. Okay, it's very important. But we can, but actually the application has many instructions. So if we find the independent instruction in this within the basic block, then we can reduce the clock count for this instruction. And then this is the example. So in this example, we can find the data dependencies from this load and add here and here, and then here and here. This load and then as we learn, this instruction pairs will consume 1 more cycles, and then also this instruction pair will consume 1 more cycle, because this add instruction requires data from this load instruction. But as you can see, there is data dependency from load and add from here to here. But if we can insert any independent instruction between this load and add instruction pair, then we can avoid the data hazard like this. So this is the optimized code. The right side code is the optimized code. How? So how about this load and add instruction pair, like here and here? We can insert this load instruction between this load and add instruction. Okay. And then, so this load instruction will consume 1 clock, but because this add instruction will be executed after this load instruction. So because of this independent load instruction, then add instruction will be executed 1 clock later. But during this slot, for this slot, another instruction can be executed. Okay, so we can reduce the required number of clocks for this optimization. So how about this pair, like load and add? So we can find the 2 independent instructions between this load and add instruction. So with this with this scheduling technique, so this is called the scheduling, and then this technique is applied by compiler. So compiler can analyze the dependencies between 2 instructions, and then if the 2 instructions have dependencies, then compiler can change the order of some instructions, and then compiler can insert any independent instructions between these 2 dependent instructions. So with this code, this code will consume 13 clocks, but with this code, we just change the order of instructions. This code will consume 11 clocks. You may think, oh, that is just the 2 clocks, but how the performance is improved? The performance improvement is 13 over 11. So you can calculate the performance improvement by this optimization. Okay. And then control hazard. So as I explained, the control hazard means that the clock cycles are wasted by branch instructions. So the BQ is here, BQ X1, X2, and target. Then the following instruction is the solve, very next instruction. And then here is the target, like add. So we don't know which instruction will be executed at the very next of this BQ instruction, right? So based on the result of this branch instruction, this very next instruction, like a sub instruction, can be executed, or the target instruction, add instruction, can be executed. So there are two possible cases. But in order to fetch the instruction from the instruction memory, then we need to calculate the program counter. And then actually this program counter is used at instruction fetch stage. It's the very first stage of the pipeline processor, right? So actually the processor does not know the result of this branch instruction. So the processor needs to wait until the result of the branch instruction is reserved, and this is called the control hazard. So actually we will learn more about the control hazard in the later, not today's class. So just to see that this pipeline diagram, like BQ is here, and then let us assume that the BQ is reserved in the ID stage. It's different from what we learned in the single cycle processor. And then because the target of the branch and then the result of the branch is determined in the ID stage, we don't know which instruction will be executed, which instruction will be fetched very next of this branch instruction. So 1 clock cycle is wasted, like here. Okay, that is the control hazard. So in order to reduce the control hazard, we can apply the branch prediction technique. So we will learn about this branch prediction technique later. Okay. So pipeline summary. So why pipeline is why do you need apply pipeline architecture? In order to increase the performance. And then with the pipeline design, we can reduce the clock period by ideally number of pipeline stages, right? 1/n. But the pipeline architecture is applied, the clock cycles can be wasted due to hazard. And there are 3 types of hazard, and then structure hazard, data hazard, and control hazard. So because of this hazard, CPI can be increased. So that means the performance can be degraded. The performance can be degraded because of hazard. So we need to reduce the number of hazards in the processors, and then in order to reduce the number of hazards, we can apply data forwarding for data hazard. Also, we can apply, we can invest more hardware resources to reduce the structure hazard, like separating instruction memory and data memory. Also, we can apply data forwarding to reduce data hazard. Then we can apply branch prediction to reduce the control hazard. Okay. Before going to the next topic, let's take the pub case. So this is the first pub case. Then, oh, I did not. So just write down the answer for this pub case, and then I will make the pub keys on the blackboard. I realized that I did not make the pub keys submission link on the blackboard. I will make after this class. But this pub keys is the first pub keys for this course. Okay. 네, 팝 퀴즈 진행해 주시고요. 링크는 말한 대로 블랙보드에 생각을 해봤더니 생성을 안 했네요. 네, 링크는 이 수업 끝나고 만들어 놓을 테니까는 오늘 그 12시까지 팝 퀴즈를 제출하면 좋겠습니다. 안 보여? sorry. Can you see? 네, 자정까지입니다. Okay. Let's move on to the next topic of the today's class. So next topic is how to implement pipeline processor. So we learned how to implement the single cycle processor. So firstly, we learned how to design the data path elements. So for this data path element design, then we just define the required input and output of each element. And then that is the lab assignment number 2. And then the single cycle processor design, we just connect the each input and output port of the data path element based on the flow of instructions. Also, we define the control unit of the single cycle processor because each data path element requires control signals from control unit. And then these control signals are determined based on the instruction formats or instructions. Then by connecting this input and output of data path elements and control signals, then we can complete the single cycle processor. The next step is to implement the pipelined processor, right? So this slide shows actually the single cycle processor design. And then when you learned about the pipeline architecture, then we divide the required stage for this required stages. When the instruction is executed by processor, there are 4 stages, right? Instruction fetch, instruction decoding, execution, memory, and write back. So that means there are 5 stages in the pipelined processor. So we just separate each stage in the single cycle processor, right? Instruction fetch, ID, EX, memory, write back. And then as you can see, the instruction memory is accessed in the instruction fetch stage. And then in the ID stage, the instruction is decoded and then register file is ready. And then execution stage, the ALU is executed. The ALU is used for operation of instruction and address generation for load and store instructions. And then the memory stage, this data memory is accessed. And then write back stage, the result is written back to the register file. Okay, so if you see this figure, then we can see how the instruction flows through these 5 stages, right? Instruction is fetched from this instruction memory, okay? And then as we learned, instruction has 3120, so it's a 32-bit instructions. And then each field is given to the input port of the register file. And then also the immediate values can be generated from instructions. And then the operands are given to the ALU, or based on this operation, the address can be generated, or result of the alt-type instruction can be generated from ALU. And then this address is given to the data memory, and then here, and then so here. the data is written back to the register file. So we just shows the single cycle processor, and then we divide the each stage of based on how the instructions are executed in the processor. Okay, 5 stages. Then how can we implement the pipeline processor? The first, we need to use pipeline registers. Oh, you may be confused that, oh, this is the register. So it's similar to the general purpose register in the processor. No. It's totally different. So this pipeline register is just a flip-flop. So when we mention the general purpose register, then that means just this register in the defined by instruction set architecture, and then this pipeline register is different, is totally different from general purpose registers defined by instruction set architecture. Okay, it's just a D flip-flop. So what is the D flip-flop? So we learned about the D flip-flop in the digital system conventions course. So what is the D flip-flop? So it's the clock. This is the input. This is the output. So what is the operation of this D flip-flop? At the rising edge of the clock, this input value is updated to the output Q. That is the operation of D flip-flop. So this pipeline register is just a set of D flip-flops. Okay, so what does that mean? So when you mention the pipeline registers, we just mention the neighbor stages of this corresponding pipeline register. So that means for this pipeline register, it's called the instruction fetch / instruction decode. So that means that this pipeline register is located between instruction fetch and instruction decoding stage. It's the same to the other pipeline register like ID, EX, so here. EX / memory is here. Memory and write back is here. So I said this is the just D flip-flop. So clock will be these pipeline registers are synchronized by clock signals. Clock here. And what is the input of these pipeline registers? These are becomes the input. And what is the output? This is the output, right? So this is the D. This is the Q of the D flip-flop. So let's see this. So this is the instruction memory. The instruction memory receives address from the PC program counter. Then what is generated? This is the instructions. And then the width of this instruction is the actually inst 31 down to 0. And then this output of the instruction memory, like instruction, is sampled by clock signal at instruction fetch and then instruction decoding pipeline register. So this is the output of this pipeline register T flip-flop. So this is the rising edge of the clock. Then this is the instruction in the instruction fetch stage. So this instruction this instruction will be generated at this point just before this rising edge of the clock here. So it is read from the instruction memory at this timing. Then what is the instruction in the ID stage? So this is the instruction fetch stage. This is ID stage. So this is the instruction in the instruction fetch stage, and this is the instruction in the ID stage. Okay. So this instruction 1 is updated. So this becomes the output of this ID stage of instruction at this timing, the rising edge of the clock. So comes the 1 here. Do you understand what I said? So this timing is very important. This is very important to understand the pipeline architecture or pipeline processor. Okay. So that means in this clock period, at the next clock here, so this instruction is given to the register file, and then the operands are read from this register file. Something like some timing here. Then it is sampled by ID and EX stage, so operand. Okay. So you need to understand what are pipeline registers. So pipeline registers just T flip-flop. So the pipeline register, the output of this pipeline register is updated at the rising edge of clock signal. And then that means that the input of this pipeline register is the output of this stage, and then this output of pipeline stage becomes the input of this stage. Okay, just try to understand. 사실 이 파이프라인 구현에서 사실 우리가 이제 랩 4를 하면서 파이프라인 구현에 대해서 실습을 하긴 할 건데 이게 학생들이 좀 어려워하더라고요. 예, 아무래도 새로운 컨셉트고 그다음에 이게 시간의 흐름에 따라 가면은 이게 보통 이제 소프트웨어 하는 사람들은 많이 힘들어하는데 예, 이런 부분들을 잘 이해를 해야 되는데 어쨌든 또 제가 이제 다음 시간에도 조금 자세하게 나가긴 할 거지만 이런 어떻게 신호가 흘러가는지 결국에는 각각의 단계를 파이프라인 레지스터로 다 나눠놓은 건데 그렇다면 이제 타이밍에 따라서 신호가 어떻게 흘러가는지를 잘 이해를 해야 됩니다. 네. 시간이 많이 시간이 넘어갔는데 예. 질문 있나요? Do you have any questions? Okay, I will stop here and then see you in the next class.